This meeting is now being recorded.
The recording will be stored in the members area of INCOSE Connect. Please be patient with us about the recording. We will get the the slides posted as quickly as we can. The recordings sometimes take a little bit longer. Now I'd like to introduce our speaker, Kent Harmon of the Targeted Convergence Corporation. Kent will be speaking to us today about how the conventional approach to systems development often fails to produce the innovative products that we want and often leads to major unplanned design loopbacks that increase cost and time to market. Kent will explain how increasing the use of simulation in the early phases of product development can prevent these problems by proving the feasibility of the system architecture prior to committing to specific requirements and a detailed design. Kent is a former engineer, engineering manager, product development manager, and director of R&D effectiveness with Texas Instruments Semiconductor Group. He has over 25 years experience leading and mentoring product development initiatives. For the past decade, he has been at the forefront of developing and implementing the methodologies to restructure the front end of development in order to reduce time to market by over 50% while enabling the design of more optimal products. Kent, welcome to our webinar, and thank you for being willing to share your work with us. If you'll give me just a second, I will stop sharing my screen and turn things over to you.
Thank you, Bob. Happy New Year to everyone. Thank you for joining me this morning, and I'd like to thank Chris Unger for the invitation to share this presentation. It was originally made at INCOSE in Bangalore last November, which Chris was also a speaker at, and I'm thankful for the opportunity to share it through another forum. Give me 1 second here while we load my screen up. I have some dots going around in a circle at a furious rate here, so hopefully here we'll be there in a minute.
Okay, now it's showing. I can see it very well.
Very good. Ever so often, more rarely than it should be, something comes along to challenge our way of thinking about what we're doing or how we're doing it. And what I'm about to share with you is a culmination of such a challenge that came to me and my colleagues about 10 years ago, when we'd been involved in improving product development for many, many years. And we came across something, and it just really changed our entire outlook about how we thought about traditional product development. There's some contact information here if you want to have questions later. Email at the bottom there is a great source. And for general awareness, there's 2 books available through Amazon that you might also want to read up on the background of this. So, in healthcare, and we've worked with a number of healthcare clients, you're looking at increasing design complexity with every new product. The competition is always increasing. There's always that need for an innovative solution to advance your knowledge, and time and budget pressures. And so with each new generation of product, we tend to want to seek out the new tools and new approaches to help us meet these challenges. And then when we look back, we see that the past designs and innovations where these challenges were successfully met now actually appear simple and obvious to us. But the ones going forward, of course, appear much more challenging. I'd like to take you back a little bit to a challenge at the beginning of the 20th century. And that challenge was to be the first in the man-controlled and heavier than air-powered flight, the airplane. And of course, at this time, we all look back, and most of the people in the world, except apparently those in Connecticut and the island of New Zealand, consider the Wright Brothers to be the inventors of the airplane. But at the time, there was actually a very fierce global competition. A lot of people were seeking to be the first. Of course, the opportunity was obvious. There was certainly fame and fortune involved there. But the risks were also apparent. Bankruptcy, injury, even death was all too real in this. Now, as I mentioned, history generally credits the Wright brothers as being the first. But if you looked at it objectively, either now or even at that time, they would have probably been considered to be the least likely to be successful. They were bicycle owners in the small Midwestern town of Dayton, Ohio. They had less education and less money than most of their competition, yet ultimately they were successful. When you stop to think about that, what can we learn from their experience? What can we learn from them? And what I believe is one of the most important observations they made occurred early in their endeavor to be first. They started looking at this and said, most of these other investigators, as they called them, we would call them would-be inventors, were spending thousands of hours designing their plane and about 5 seconds testing it before it crashed and sometimes killed them. And their response was basically, hey, we're a couple of simple country boys, but this doesn't sound like it's very smart to us. So what they did instead is they decomposed the problem of flight into 3 critical functional areas of knowledge: lift, control, and propulsion. And the first thing they did was focus their efforts on developing methods of experimentation and learning all they could about these 3 areas. And so they employed scaled kites and gliders, a wind tunnel. They created their own instrumentation to measure airfoil models in that wind tunnel, and they meticulously recorded all the data, and even employed a very new technique at the time, graphing. At the time, most engineering work was recorded in tables because it was easier to put in typeset. And the thing that I found most interesting is that in the 3.5-year project that they worked on here, the design on the full aircraft did not start until 6 months before they flew. And what I find very amazing is what the 2 Wright brothers, along with their bicycle mechanic, Crawford, were able to do in a part-time effort, because they had to run their bicycle shop, between May of 1900 and December of 1903. They discovered that the lift and drag calculations everybody else was using was incorrect. They discovered optimum wing shapes and control surfaces, actually in 3 dimensions, something that hadn't been done before. And while that there was no production engine with adequate power and low enough weight, they eventually invented those. They invented a wind tunnel and the mechanisms for measuring lift and drag, a wing working technology for controlling the plane in flight, a highly efficient propeller. And the aeronautical customers that we've worked with told us that for a fixed wing propeller, there has only been a 3% increase in efficiency since the Wright brothers' original design, which I find incredibly impressive. And they developed a lightweight engine and the entire science of aeronautics. And as I look at that list, I'm thinking to myself, I would be happy in my career if I had just been able to do one of those things. And yet that was all achieved in a 3-year part-time effort by 2 bicycle mechanics with a high school education. What's more impressive is when you compare it to what was perhaps their top competition. Samuel P. Langley He was the head of the Smithsonian Institute in Washington. He was considered the world's expert on flight. He was the one that everyone would say would be the first to fly. If there was somebody wanted a speech on the potentials of manned flight, Sam Langley would get the call. As a result of that, he got $70,000 in government money to develop a plane for the Navy. From that, he put about 17 staff years into the plane. His approach was, well, I'm an expert. Here's what the plane design needs to look like. They would build it. He would hire a test pilot. They would test it. They would pick up what pieces they could out of the Potomac River, and they would start again. For 17 years after the Wright Brothers flew, different people tried to get the Langley design to fly so that they could validate the Wright Brothers patent. They were never successful. Now compare that to the Wright Brothers. No exact records are available, but it appears that it was something like 22 months of effort over 4 years, about $1,000 of their own money, but their method was very different. It was test and experiment, test and experiment, test and experiment, until they fully understood what they were doing. Only then did they design and build the aircraft, and of course that first design was successful. So usually in a live presentation at this point, I ask everyone, okay, we'd all like to be more like the Wright Brothers, but how are we actually executing in our businesses? And I'd like you to think just where in your process does most of the testing occur? Is it before or after the design? Maybe everyone could just pop in on the chat and answer the question, is your process closer to Langley or the Wright Brothers? That'd be kind of interesting to see. But this approach that the Wright Brothers took actually offered them a supreme confidence. 2 days before their first successful flight, they telegrammed their father, and the key words we saw in that telegram were success assured. They knew before they would fly that they would be successful because they built the requisite knowledge to be successful. And it was from this systematic learning that they performed on understanding the limits and trade-offs of all the different concepts and solutions that were possible. The other thing that is notable about how they approached it is they did not start off saying, well, I think this is what the design needs to look like. They delayed decisions on the final design until they fully understood all those limits and trade-offs. And I think that is the key thing that came to us when we were thinking 10 years ago about how product development is being performed. Because let's go back in a little history. If we look from the Wright Brothers on, for about the next 80 years, a lot of product development was performed using the Wright Brothers approach. It was the de facto standard in aerospace for sure. And it consisted of a lot of early in-process research and testing, lots of trade-off curves. These would be systemized into what was called nomographs. The way to think about that is a problem-specific slide rule or mechanical computers. If you've ever taken a private pilot lesson, I don't know how they do it now. They may do it with GPS, but it used to be a radial mechanical computer that helped you plan your RPMs, your fuel usage, and your distance. Then around 1980, computer-aided design became prevalent. And I was actually in the semiconductor industry, there when we shifted from the mainframe to the mini computer and finally to the desktop, all in the span of about 4 years. And it had the promise of speeding up the drafting process, particularly with 3D modeling. And then once we had those models available, we say, hey, we could use the geometric input we get from the drawings to simulate the physics or the performance of these designs. And so we begin to simulate the performance of those designs. And the next kind of evolution was around 1990, when we began formalizing product development into standard processes. Prior to that, there had been a big push for quality improvement with what's known as total quality management systems. ISO 9000 and so forth came out of that eventually. There was a push for business process re-engineering, which was an outshoot of the Toyota production method. Somebody at Harvard named Michael Hammer said, hey, if standardized manufacturing processes are good, then we ought to be able to standardize the back office, the white-collar jobs, and get the same type of results. So all this confluence led to these detailed product development process, phase-gated processes. The ideal behind all of that was let's be more productive in product development by making it look more like manufacturing. And of course, we know that that's probably not going to work out well because there's some fundamental differences there. And yet, and that's what we found. 25 years later, unplanned design loopbacks are still consuming, we find when talking to our clients, about 50 to 75% of the resources in the organization. Late firefighting, unplanned work, reworks, so forth and so on. A thing that, and I was aware that existed. What really surprised me was when we started looking at product development from a different point of view and applying some different engineering techniques, we found that products that we thought were optimal were far from optimal. I've seen things as much as 40% performance improvement on some things as mundane as parking brakes and underarm deodorant merely by changing the way we looked at product development with existing technologies. It really surprised me. And find out that there is a good reason for that. And probably don't have time to go into that today, but that what we continue to find to be the case. And the other thing that struck us is how much knowledge we lose as during this process. I know that my work at Texas Instruments, we had a lessons learned database. And our detailed phase-gated product development process said that before you can release your product, you must go and update your lessons learned database. And so, of course, by the time we got to the end of the project and trying to get the product released, we'd already be assigned the next 2 projects to work on. So we spent very little time actually putting things into the lessons learned database. And then the next project said, hey, you got to go check the lessons learned database before you can get started. Well, we do that to get the checkbox, but we knew that we'd put garbage in, so we only expected to get garbage out. And I don't know if anybody else works like that or has had that experience, but basically in product development, in most places, the only way you get that knowledge transferred from one project to the next is by transferring the people. And of course, that limits your ability to fan out to more than one project in the future. And of course, you have the risk of losing that knowledge as people hit the lottery and other life changes. So what is known as the fuzzy front end was causing a lot of these problems. It was result ultimately from premature and ultimately unsuccessful decisions. And if you think about your process, you're making a lot of very important design decisions very early, from which opportunity to pursue, what the requirements are, which technologies to use, what to innovate, the basic system architecture, the technical decisions such as materials, components. Hey, how are you going to get the cost estimate for the business plan to get the project approved unless you've already decided on these things, right? So the motivation is to decide very quickly. We want to reduce the scope of the project. We want to create detailed plans and costs so that everybody feels good about pursuing the business and that we're confident there. We need to show that we've got confidence in a good return on investment. And in the back of our minds, often not spoken, we know we need to get started because we're going to have a bunch of design loopbacks and we need to have time. So another question I might have for you is how many people actually put those design loopbacks in your project schedule at the front of the project? Just curious. So what we may have done in our efforts to be more productive is we moved from Langley's design, build, test, and repeat to the Wright Brothers' very successful learn, repeat until their success is assured, design, build. Then along comes computers. So what we do instead of using them to help us with the Wright Brothers is we basically create computer-aided Langley, where we create the geometric design, we build software models, we simulate, we repeat, we build prototypes, we test, we repeat. And then, of course, that's not working well, so what we need is more standardization and regulation. So we start inserting review and approve, review and approve, review and approve between each step. I know it comes across as I'm slamming it, but I was at the forefront of this right here at one time. If I had come across you at that time and encouraged you to do a standardized process, I now apologize for having done that. And there's some benefit to it, but there's some weakness also. Let me turn now, if I can, to an aircraft design as an example. Just going by the standard textbook for aircraft design by Brandt, Stiles, Burton, Whitfield, they describe the process as multiple iterations through 12 activities. We depicted them here for them. These are the ones they list out. I'd like you to note about what goes on here is to get some customer requirements in. They synthesize the design with the goal of optimizing the customer focus. Well, how do they do that? Everything starts with geometric modeling. And from that, all these other analyses must be performed. Aerodynamic, propulsion, constraints, mission, weight, sizing, cost. Each of these subsystems report back in. They synthesize the design and recheck it. Okay? And this is certainly an iterative process. And what's worse is because each of these subsystems are dependent on the outputs of the other subsystems, there are long wait times. Weight analysis has to wait for propulsion modeling to finish, and sizing has to finish for weight analysis, and then there's all these built-in loopbacks, even through the simulation process. And this scenario is not isolated to aircraft. It's pretty common in many of the complex systems we do. I won't go into detail, but it's certainly true of something like cardiorhythmic management devices. Also, susceptible to the same type of interactive analysis. And so what we have is a big loopback. And everything passes through that geometric modeling. So what we're basically doing is we're hypothesizing the final solution. And maybe it's a good hypothesis. We use our experience. We use our knowledge. We try to get a lot of smart people together, and we try to come up with the best solution possible. And then based on that geometric modeling, including perhaps technology selections and material selections, each functional subsystem then builds specialized models based on that to simulate the performance. We come back together, we synthesize it together, and we make adjustments, and we repeat the process. Unfortunately, usually we'll get there, but it's not guaranteed. And what is certainly not sure is we're not sure how many interactions it's going to take to converge. Now let me put a opposing hypothesis out there. Suppose that instead of starting with geometries and the concepts and the properties being the input to the analysis, suppose they were the output. Suppose that instead of coming with the mindset of how do we prove one specific point solution is going to work, our objective was instead to eliminate everything that wasn't a solution. Now there's a subtle difference in description from picking one and proving it works to eliminating everything that isn't. But it is a complete paradigm shift in how things work in your thinking, how your thinking changes when you make that switch. And once we have that feasible set, we can just optimize within known feasible solutions. Typically, and I'm sure you've heard of this is set-based concurrent engineering. There's a formal definition I'll let you read. It's basically the goal of eliminating the weaker alternatives by concurrently looking at all the trade-offs. Okay? And there's a lot of misconceptions out there about what set-based concurrent engineering is. I'm going to try to clear up a few of those. The first thing that pops to everyone's mind is that we don't have time to look at one alternative. How are we going to look at multiple alternatives? There's when you understand what it is, it becomes very apparent that it's actually quicker than looking at one solution. The things that need to be done are, of course, we need to rapidly identify and close knowledge gaps that prevent us from knowing which are the weaker or infeasible alternatives. And then we need to define the bounds of the feasible solution by systematically eliminating the infeasible, not by looking at all the feasible ones or all the possible feasible ones and seeing if they are. And then we want to make the tightly related trade-off decisions concurrently so that all the things that affect each other, those decisions are not sequential so that we wind up going down a maze of which there's no return, but that we make them concurrently so that we're assured of a system-level solution. And that we want to do all this with visible knowledge, not with assumptions, opinions, unproven hypotheses, wishful thinkings, and so forth. So I'll put set-based concurrent engineering in a nutshell for you. It's all about the curves, okay? This was a major epiphany to me because when I first heard of set-based concurrent engineering, I thought it meant building multiple full products or full subsystems and fully testing. Now, it's about the curves because there are an infinite set of points on a trade-off curve or under a limit curve. And what we are infinite interested in is that infinite set of feasible solutions that are at the intersection of our design goals and our technical feasibility. And so what we're talking about, conceptually at least, is being able to stack up all the trade-off and limit curves that affect each requirement and then compare it to the acceptable range. Okay? Now, the question becomes, which curves do we need and how do we stack them up? This is what we call a causal map. It was the answer we came up to that question. I'll explain the map here a little bit for a second. The circular nodes are what we call the technical decision nodes. They're variables for most parts. We call them decisions because it's a more generic name, for one. And two, we want everyone to be conscious that they are decisions. In those nodes, behind them, we would capture what alternatives exist. And those alternatives might exist as a set of discrete values like materials, or as a continuous function like some dimension. The other thing we want to think about is our requirements. What we commonly call requirements are also a decision. We, as engineers, get to decide if and what and how much we will meet those requirements. In some cases, I can argue it would be good or better not to accept the requirements that are handed to us. But that's a discussion for another day. In between those decision nodes is a node, the rectangular nodes we call relations. They basically are the transfer function between those decisions. And they could be a curve, they could be a table, they could be a best practice, but they basically are, if you have these 5 nodes connected, what happens when you change them? What happens to the other when you change 1, 2, 3 of them? And what we're interested in there is knowing how these decisions trade off and how they're constrained or limited. Now, this model you see here, this causal map, is actually for aerodynamic analysis of an airplane. One would have thought it would have been more complicated. And when we sit around and talk about it, it sounds more complicated, but when we reduce it to simply the cause and effect relationships that form the trade-offs and limits, it actually becomes much clearer. And with on here, I also want to point out these pink nodes. We can identify these are areas where we may not have enough knowledge to actually form a decision out of this. These may be knowledge gaps between us. So we can actually look and see, like this cloud, we don't understand what that relationship is, perhaps. Okay. So if we wanted to look at the aerodynamic portion, we could add to it wing area, propulsion, weight at takeoff, cost, etc., and actually look at the trade analysis for an entire mission load. Again, coming in much simpler than one might have imagined from the start. If we are able to make those relationship nodes analytical in some way, whether it be through equations, interpolated data, logical operators, maybe the output of another type of simulation, then the opportunity exists to be able to simulate this network for all the sets of decision alternatives. And by decision alternatives, I would give you an example. One of the nodes might be wing material, and it might have 3 or 4 different alloys of aluminum, plus maybe carbon fiber is alternatives for making solutions to that. It would be the multiple choice answers to the question, what will our wing material be? So if we have that capability and do that, that would provide us an opportunity to look at that design space through computer-based simulations very early in the process. I would point out to you, this can all be done very quickly, very early in the process. And what it turns out, the testing requirements actually become pretty small, because as we make visible what we know in those causal maps, it turns out that our knowledge gaps are, one, smaller, and two, much more focused than they were before. So we're able to do much more focused testing, much more limited testing, and we're able to actually build an analytical model that we can use for computer-based simulation within it. And the outputs might allow us, this is the network I showed you for emission analysis. This would be 4 different visualizations of that same network, depending on what you wanted to see. That would depict, for example, up here, based on different choices of decisions within that network, what the feasible space is, some major trade-offs, trade-off areas, if you would, here where we have a line here, we have an area here, and even optimization type of algorithms could be used and employed against that network. So let's see here if I'm running out of space here. So in conclusion, with or without computer-based simulation assistance in conceptual design, we would recommend a set-based design approach that emulates the Wright Brothers by moving all that learning to the very front end of the process. We replace that fuzzy front end of the process with very focused and specific learning, targeted at understanding all the trade-offs and the limits that the decision criteria or the decision focus change from being, oh, what is the best one and how do we prove it, to let's first eliminate everything that isn't a solution. Let's first eliminate all the infeasibilities based on actual data and facts. And that any approach, some standard visible model be employed to bring together the integration of the subsystems. We believe that causal maps provide a great Rosetta Stone for bringing together the different subsystems, because they can see how the decisions they make affect each other, and they actually uncover interactions that they didn't understand before and knowledge gaps that they weren't aware of. That we'd also recommend that any computer simulation should allow the use of any form of analytical knowledge as input. And that's one of the limits to, it's one of the causes of interoperability among simulation models, is in many of them you have to have an equation, or some don't handle interpolated data as well as others. Knowledge in whatever analytical form should be available as an input. And then a recommendation for any computer simulation from the concept should allow the users to actually look at that n-dimensional space from multiple perspectives, the way they want to see it. And so we are seeing a number of people we work with actually employing this to great success now. And I think I've reached my time limit. And so, Bob, were there any questions that popped through as we went through this?
Well, first I want to thank you for the really great presentation. I certainly enjoyed it. We do have a couple questions in. One was, does a choice at one relationship change the shape of the curve between your decisions?
If that choice was, say, a technological concept, a technological approach. You go from battery to nuclear power, you're probably going to get a whole different set of curves, right? So it can have, that choice can actually, if it's technological in nature, change the architecture of that map and the content of the curves. However, since that's a cause and effect relationship, within a technology, what we find until you change a base technology, generally if you add a material, you're just adding one or two curves to those relationships. The actual interactions remain the same. So that becomes a very powerful starting point for the next project. You can very quickly check to see, hey, do we have an existing solution? If not, specifically, what is limiting us? Which of those curves is the limit? And this is something that's come to look at. If you, I remember sitting in debates about what is innovation. And to me, innovation is now simply moving the curve in the direction of greater customer value. And if we bring into it the from networking theory, that in a network such as this, at any one time, there is only one constraint to the output, to any particular output. What this allows us to do is find the exact core trade-off or limit that is keeping us from adding greater customer value. Now, there may be another one right behind it on some other place, but at any one time, there's only one. And what this allows us to do is very specifically focus R&D. Okay? And that's quite powerful when we get to do it. A second thing I found was from chief financial officers. I don't know if anyone in the audience has this problem, but the chief financial officer at Texas Instruments threw around nickels like they were manhole covers. And an argument from an engineering manager or product line manager along the lines of, we need this, trust me, didn't carry a lot of weight. But what you can do with these maps is you can actually walk a CFO or someone of that nature through it, and they understand it. And I've had them tell me that and say, okay, now I understand why you're doing this test and how it relates to the marketplace and the customer value, because it connects it all together in a very logical, visual way that they can understand. So there's just so much tremendous value in getting that consistent standard vision model out there. Even if you don't ever make it analytical, that you just use it for collaborating around what the trade-offs and limits are, so that you can, everyone on the team and across the functional areas and the subsystems and even into finance and marketing can understand what's going on.
That part about presenting to the non-technical decision makers is really critical, because there's always a wish list that far exceeds the resources available. And the challenge to the decision maker, whether he's a CFO or a chief engineer or whatever, is, okay, which of these really are going to make a difference to my ability to have good products in the marketplace? And so, being able to show those connections is really critical. We had another comment come in. It says, this formulation is very similar to the target selection process in military intelligence. Dynamic programming finds the better subset even when the success at one goal changes the importance of subsequent goals. Do you want to make any comments about the dynamic programming process?
Sure, I do. My master's degree is actually in engineering management and operations research, with a very heavy operations research thing. And part of that, of course, is decision algorithms. And one of the great disappointments in the product development process that I always talked about earlier is manufacturing is a deterministic process. Other than natural variation within process step, it is a very static, deterministic process. In other words, you do the same steps every time. Product development and innovation is a stochastic process. every one of them is different. You do different steps every time, and you do each step differently different times. In operations research, including the example with the target acquisition and other things, is for stochastic processes, you use things like branch and bound techniques. This is very similar to a branch and bound technique. There was a book written in the 1990s by an Austrian psychologist named Dietrich Dornick. It was named The Logic of Failure. And he was puzzled by the question, how did the smartest physicist who wrote the safety manual for the Chernobyl nuclear power plant manage to melt it down and kill themselves? Okay? And it was a very powerful question. And what his conclusion was counter to, of course, it was the manager's fault. What he found was they had a dynamic situation and they started making sequential decisions. And each sequential decisions took them to a place that made it harder to recover from and forced another sequential decision. So that each decision in its own looked right at the time, but the pattern of sequential decisions led to catastrophe. And his conclusion was he listed a principle that says that, actually the primary human decision factor is, of course, to theorize a solution and go prove it. He said, however, in complex situations, the third most prevalent human decision making process, which is this basically set-based concurrent engineering, it's let's learn as we go and eliminate things that don't work, is actually the more optimal. So my take is anytime you're in a stochastic process, you have a lot of uncertainties, it's complex. That decision approach of learning and eliminating the non-solutions is much more efficient in the long run.
Okay, we've only got time probably for one more question. We had one that asked, can you address the challenges of getting all relevant knowledge into analytical form and identifying the causal interactions when dealing across domains like social, cyber, physical, human systems?
All right, there's two parts. I'm going to take that in two parts. One is just a general question of getting the data and the causal relationships. What we actually find is that the data mostly exists somewhere. What is lacking is kind of the collaborative understanding of all those interactions in the visual model. Because we typically talk about the things that are on the drawing, the bill of material, and the customer requirements. And everybody assumes that everyone's thinking the same way about all those interactions in between. It turns out that's not the case. In fact, most of us, when we think we have, and I've experienced this myself when I sat down to do some things that looked pretty obvious to me, that I really didn't have as firm a grasp on those interactions as I thought I did. That's also actually turns out to be more difficult than getting the data. The data, I've seen people, when I do a 2-day workshop, go out on the lunch hour and get all the data they needed in the lab. So most of the data actually generally exists or can be found quite quickly. The important thing is getting those interactions. The second part comes to what some people call, I think, the tacit knowledge or the physical interaction or human interaction type stuff. And one of the things here that we want to do is we want to focus on being able to get something measurably or at least repeatably scoreable. I work with a company, I think I may have mentioned it, does underarm deodorant. They're actually able to have a body of, or a panel of calibrated noses that are able to give repeatable, credible results on body odor. And so what we generally find is that we just haven't thought hard enough about how to make some of those things that we put in as human interactions measurable. We haven't dedicated the time to it. And I've got, if we had longer time, I could give many, many more examples of that. But the thing we want to do is to give some thought about how we measure or make standard. The other thing you want to note here is since that we're trying in the concept phase to eliminate the infeasible, you don't necessarily need 9, 10, 20 decimal points of precision, okay, on this stuff, right? Because what we're interested in doing is keep creating a fence, and you don't have to be that precise. So that also reduces a lot of the testing load.
So any thoughts about what happens when you cross domains? I mean, the example you gave from the aeronautical industry was great, but it did mostly focus on things relative to, I mean, those are all pretty closely related phenomena. What happens when you start mixing cyber and human systems and stuff like that?
When we get to the standard model, when we start seeing what we call them interface decisions, those decisions that are shared across those boundaries, we start describing and articulating that. We can generally focus on it and get very specific, so that those decisions that are shared, we call them interface decisions, are often the purview of the systems engineer. We just need each of those specialty function areas to be able to feed the trade-offs into those nodes, so they can actually work in their own language as long as they come together at those critical interface nodes. And
that makes a lot of sense.
The software and hardware is pretty easy on that regard. Is there another factor that someone's alluding to there that I'm missing that you want me to address?
No, I think it was just the whole idea of when you start crossing those boundaries where you have very different expertise, how do you capture them? And and you've highlighted that you highlight those connections explicitly in your model, and then use them as the focus point for getting the multiple domains to work jointly together. So I think you've answered the question.
I've personally become very committed to the ideal of using visual models always, first and always. If it's nothing but stick drawings, it solves so many communication problems. In fact, I now believe it's impossible to communicate without visual models. Or not communicate, but collaborate, certainly. It's impossible to truly collaborate without visual models. Because I've run into cases where people have worked together for 10, 15 years. Very, very talented people, very, very knowledgeable, very, very specialized, worked together in the same area on the same product for 15 years. And you get them to sit down and draw the picture of something that they're both using the same words for, and they come up with something different.
Oh, yeah. Certainly I've seen that in many situations where very heated argument about the same words, and then eventually you find out, well, that's because they meant two different things by those words. And certainly that's one of the areas where systems engineers are supposed to have a strong role in terms of sorting those out so that people, when they do argue, and they will, they'll at least be arguing about the same thing.
I always start at the marker board or flip chart with a pen, and everybody, let's draw a picture of this. That's the first thing that we need to do, whether it's a free body diagram, a flow chart, a photograph, whatever. And that, if you start that practice, that will help bring together, the cyber and the hardware and the physical interface and all that other stuff, because you'll start to break down those nomenclature barriers. Yeah.
Okay, well, we've run a couple minutes over, but I think that's because everybody was interested. Again, Ken, thank you very much for a really great presentation, and my thanks to everyone out in webinar land for tuning in and for sharing your questions. We'll be having another webinar next month, and those of you on our mailing list, you'll get the email, And if you're not on the mailing list, keep an eye on our LinkedIn site. Both of those are good places to stay up to date. Okay, thank you.
Thank you.